Okay, so big tank of water, pipe draining the water, water comes out on the right side. We're going to assume that up here, I'm going to call this point 1, that because it's a really big tank, that the water level's not going down fast enough to matter. In other words, I'm going to make the claim that the velocity of the water there is equal to 0. And the thing that we want to do is we want to figure out how fast the fluid is going when it leaves down here. And then later on we're going to ask what is the velocity of the fluid when it's like right there. So what's the velocity at these points, basically? We'll start with the simple one. We'll start with point 2. Now the reason that I picked those 2 points is because I know what the pressure is at those 2 points. For the very tippy top water molecules, over there at the top of our big tank of water, what's the pressure on those guys? 1 times 10 to the 5th. Why? Just due to the atmosphere. And so I know the pressure on those guys at the very tippy top is 1 times 10 to the 5th pascals. Down here at point 2. What's the pressure on those guys as they leave the pipe? 1 times 10 to the 5th. When they leave the pipe and they become, what will the water become when it leaves the pipe? A what? Projectile. Now the water behind it's no longer pushing it. And so the pressure on the last molecule to leave the pipe over here will be the same as the atmospheric pressure. So question. Between point 1 and point 2, is energy being conserved? So go back to Bernoulli's equation. In Bernoulli's equation, what's the term that is doing work? Pressure. Pressure is the term that's doing work. So if the pressure is the same, so pressure is the same between point 1 and point 2, that means going from point 1 to point 2, our energy is being conserved. Energy is not being conserved going from point 1 to point 3. Because at point 3, there's going to be a pressure bigger than 1 times 10 to the 5th. But it is being conserved between points 1 and points 2. So if I want to know what the velocity is down here, basically it's a conservation of energy question. So let's go back here and let's rewrite Bernoulli's equation. Because I'm awesome, I can just copy it like this. Maybe not. There we go. And what can I do to simplify that? Not yet. What do I need to get rid of first? You guys just told me that are the same between... Pressures are the same. And so if you're adding the same pressure to both sides, then you should be able to just go ahead and cancel it out like that. So when you do that, don't just scratch it out. Scratch it out and indicate that it's because the pressure at both points is 1 atmosphere. Now there's one other thing that I could cancel out of that equation. Not yet.
Gravity.
No, there's not a gravity term in there. I mean, what else is 0 in this picture? Oh, maybe I should do this. let's say that this height difference is like 2 meters. What would you call this height down here?
0.
Yeah, I would make that height 0. And that way this height up here at point 1 would be 2 meters. And so if I can do that, and this is usually the case, when we have a height, make your lowest height 0, make your life a little bit simpler. So let's say that the height at point 2 is 0. Okay, so now my equation becomes a little bit simpler. Oops. Oh, I forgot. There's one other thing we can get rid of that's 0. Which velocity? Yeah, so we're going to assume, and this is a pretty safe assumption, and it's a necessary one for us, that a tank like this, that the velocity here is 0. And the reason we're going to make that assumption is because if the velocity is not 0 or something constant, then that V1 is not a number, it's something that's changing over time. And when something is changing over time, that's when you have to use calculus. So that's what's going on over there, and here we stick to the not calculus form. So we're going to make that assumption, and so let's scratch that out real quick. And so I can scratch that out. Or even better, I can do that. Oh, come on. Alright, why are you... trying new things? So anyway, you pencil-oriented people should have something like this. That'll look better. Okay, now what can I do? Cancel out in there. Cancel out the densities now. So I don't want you to cancel out the densities when you're still up here, because I want you to make sure you get rid of the p's first, because if the p's aren't the same, you can't cancel out the density. It's not going to affect the velocity at a given point, but it will affect the pressure at a given point. Okay, so doing some quick arithmetic and algebra here, you would get something like 2h1 square rooted equals v2. That look familiar? Saw that a lot last year, didn't we? Something sliding down a ramp, for instance. And so if we plug in that height, 2 times 10 times 2, that'd be like the square root of 40. It's like 6 something. I got an exact number. 6.3.
Yeah.
And that would be meters per second. That's kind of cutting me off there. Okay. Easy problem, hard problem? Relatively easy. What? Right. So what's the thing you had to realize? Pressure was the same on both sides. So let's go back to our picture. So down here, we now know that the velocity at point 2 is 6.3 meters per second. Let's not even worry about point 3 yet. Let's just come back to right here. Conceptually think about it. Now at this point, I'm going to make the claim that the area of the pipe down here doesn't change. Keep it simple. At this point back here, what is the velocity? 6.3. How do we know it's 6.3? So same area, meaning the equation of continuity tells us the same velocity. We agree with that statement? So what did you expect the pressure to be there then? Same pressure? Okay. What would you expect the pressure at point P to be? I'm going to make the claim. I'm going to come back in here. I'm going to put some areas in here. Let's say the area of the bottom pipe was 0.1. And that the area at point 3, let's say it's like 0.5. And again, just for simplicity's sake, let's just say that that's 1 meter above 0.2. So would you expect the pressure at point 3 to be smaller than 1 times 10 to the 5th or bigger?
Wait, the pressure or the velocity?
The pressure.
Bigger, yeah, because the velocity is smaller, so pressure will be bigger.
So if the velocity gets smaller, pressure goes up. What other factor is there to think about? All right, so which point is deeper? Point 2 is deeper. So there's 2 competing factors here, and that's what I kind of want you to realize. There's the velocity factor. Faster velocity means lower pressure. And then there is the depth factor. Deeper means higher pressure. So we can't just make a direct comparison between point 2 and point 3. We actually have to go back and do the math, figure out what that pressure is going to be. So let's do that. Let's get forward a little bit. What would you need to figure out before you can actually figure out the pressure at point 3? Need the velocity. How would we do that? Yeah, use your A1, V1. Actually, I'm going to do A2, V2 equals A3, V3 equation. So that's just continuity. Once the water is moving through that pipe, the volume flow rate is going to be constant. And so V3, A2, V2 over A3. So let's go back real quick. My areas were 0.1 and 0.5. And our velocity V2 was 6.3. Like that. About what?
1.26.
About 1.3. So basically a fifth what it was at 0.2. Now that we know what the velocity is, now we can find the pressure at that point. So to do that, we've got to go all the way back to Bernoulli's equation. Whew, it takes a long time to write, don't it? Is there anything that I can get rid of in this situation?
Velocity of 1. Which points were used out? 2 and 3, or that's what we're trying to find?
So that's a good question. Which 2 points
2.
should we use?
We'll use the one we use. We use 1. No, we need.
So I would use 0.2 to figure out what's going on at 0.3. And the reason why, we made the assumption that the velocity is 0, which is a valid assumption, but it's not really 0. And if we put zeros into equations, sometimes they mess things up, and they will in this case. So we're assuming it's really, really small, which doesn't mess up finding 0.2, but it would mess up finding out what's happening at 0.3. We just leave it at 0. So let's use points 2 and 0.3. So I'm going to go back over here. Instead of the 1s, I'm going to put 3s. Good point. Okay, so the thing that I can probably cancel out, same thing as we did over here, I would make the height at 0.2 be 0 again. So I can scratch out this term. But everything else has to stay in there. And so if I'm looking for P3, not going to change the P2 plus 1/2 rho V2 squared. But all I've got to do here is just subtract those two terms from both sides. So it's like x plus 3 plus 9 equals a bunch of stuff. Just subtract the 3 and the 9. Same thing here. And so you might write that like minus 1/2 rho V3 squared minus rho GH3, like that. This looking kind of complicated. Because you got a bunch of terms. And your substitution is going to be kind of complicated too. So you might consider, making some simplifying things when you do your substitution. For example, P3 equals P2 plus. Do you notice that there's a row in every other term? So to make your substitution a little bit simpler, you might just go ahead and factor out that row. And then notice there's a 1/2 in the first two terms. You might factor out the 1/2. And then at the end of all this is the minus GH3 thing. Now it's just a slightly complicated arithmetic problem, yeah? So those of y'all that tend to make mistakes in the calculator thing, please take the time to write it out. Oops. So you get P3 equals, P2 is still 1 times 10 to the 5th plus, I'm not going to write units just to save myself some space. We haven't really talked about what kind of fluid this is yet. So the fluid pressure is going to depend on the density of the fluid. Let's assume it's water. So the density of water is 1,000. And then 1/2, we've got 6.3 squared minus 1.3 squared. And then minus 10 times 1. And then close that bracket out. So grab your calculator, see if you can crunch those numbers real quick. Okay, so trusting y'all, 1.1 times 10 to the 5th. And then let's go ahead and put our units back in there. And so that's the pressure at point 3. So to kind of go back to my original question, like 20 minutes ago, going back to this diagram, did the pressure at point 3 end up being bigger or smaller than at point 2? A little bit bigger. And so the pressure at pressure at point 3 was slightly greater than the pressure at point 2. So in other words, the difference in depth overcame the difference in velocity. So the other way around. Smaller velocity overcame the difference in the pressure depth there. So last question for this example. We've been on this example for like half an hour now. Suppose that Paul came along with like a little needle and he popped a little hole in that pipe. What would happen? Griffin says water is going to come out of the hole.
Top's open, so it's like with the 3 hole.
How many of y'all agree water is going to come out of the hole? Okay, I would tend to agree. Water would come out of there. There's water coming out of the hole. How do we know water is going to come out? Right, pressure at that point is greater than the pressure due to the air. Now, what would happen if the pressure there was less than the pressure due to the air? Water would not come out and air would go in. And that's how you can create things like a vacuum. Make the water go by that little point real fast, and then air is actually going to go in there. Now, the complication that may cause in real life is that would probably cause turbulence right there. So, Paul, if you do like jam needles into random pipes, try to make sure they're nice and smooth so that we don't get any turbulence from it. Will do. Okay.